Hello everyone, I'm Xiaozhi Wang, a first-year PhD student from Tsinghua University. Today I'm happy to introduce our recent work, Neural Gibbs Sampling for Joint Event Argument Extraction. This work is in collaboration with the guys from WeChat AI. At first, I will briefly introduce the event argument extraction task. Event argument extraction is the second stage of event extraction. In event extraction, we first detect event occurrence from text. That is, to identify the trigger words and classify the event types. This is the first subtask, event detection. And the second subtask, event argument extraction, is to identify the entities serving as event arguments for the detected event. In this example, that's the acquisition. And then classify their argument rules. As event detection is relatively well studied in recent years, event argument extraction gradually becomes the bottleneck of event extraction. Existing works on event argument extraction merely do argument extraction independently or sequentially. In the independently extraction methods, they classify each argument as they are totally independent of each other. Formally say that is, let xi denote the random variable of the S argument candidate. The independent extraction methods are in fact modeling the distribution Pxi given O, and the O denotes the observations from the event mention. Another typical method adopted by existing works is to sequentially extract event arguments. They sequentially classify the event arguments candidates by a specific order, mostly from left to the right. For example, first classify folks as seller only from the text, and then classify entertainment businesses as an artifact, given the text and the determined argument rule for folks, and so on. The distribution they are modeling is autoregressive. That is to say, the Px1 given O, Px2 given x1 and O, Px3 given x1, x2 and O, and so on. We claim that the above two ways cannot sufficiently model the correlations among the event arguments and the argument rules. In fact, the random variables for the argument candidates follow a totally joint probability distribution. Every event argument may correlate with each other. For example, in the sentence, it will be much easier to recognize that the fox is a seller if you have known that there is an artifact and a buyer in the sentence, and vice versa. However, obviously, it is intractable to directly model the joint distribution. Here comes our model, Neural Gibbs Sampling. The basic idea is an effective Bayesian inference algorithm, Gibbs sampling. It can effectively estimate the joint distribution with the marginal conditional distributions. Specifically, it defines a Markov chain in the space of variable assignments, whose transition distribution is the conditional distribution for each random variable, given all the other variables. It can be proved that the stational distribution of this Markov chain is the desired joint distribution. Hence, we can use Monte Carlo methods to sample from the joint distribution and also estimate the joint distribution. To raise the conditional distribution and the prior distribution for initialization, we train two neural models so that our NGS method can combine the advantages of neural networks and also the Gibbs sampling. Moreover, considering it is too time-consuming to reach the convergence with the original Gibbs sampling method, we introduce a simulated annealing method to accelerate to speed up the convergence. This is the overall framework for our neural Gibbs sampling method. We train two neural models, Note that our neural Gibbs sampling method is agnostic of the model architecture and then starts from the first prior neural model. The prior neural model independently classifies each argument candidate, as most of the existing works do. It is trained in the conventional way and is used to predict an initial argument rule for each of the argument candidates. Then our Gibbs sampling method starts with the initial state. And the second neural model, the conditional neural model, is to model the conditional distribution Pxi given all the other random variables. That is to predict an argument rule given the text and all the other event arguments labels. So in the training, we feed all the argument rules predicted in the last time step along with the text into the model and ask it to predict the argument rule for a specific given event argument candidate. The conditional neural model is used in the transition. And to improve efficiency, we use simulated annealing in the transition to select which random variable should be updated in this time step using the conditional neural model. In each time of transition, we randomly sample the variable index I following this distribution. And the C is a time-varying parameter to control the sharpness of the distribution. With C decreasing, the algorithm more and more tends to transit in the max likelihood way, and will quickly reach the max likelihood state. When at the very beginning, the C is large, and the simulated annealing will also perform like the original Gibbs sampling, so that we can avoid falling into some suboptimal results. To evaluate the effectiveness of our proposed framework, we conduct experiments on two widely used datasets, is 2005 and TechKBP 2016, and report their precision, recall, and F1 scores. We try to model architectures, DMCN and BERT as our neural models architecture in the experiments. Note that as our model does not involve the event detection stage, so in the evaluation we use the triggers and types predicted by the basic model DMCN and DMBERT for our CNN and BERT-based models respectively. Here is the experimental results on the most widely used is 2005 compared with various state-of-the-art models. We can see that our NGS-CNN and AGS-BERT achieve significant improvements over their basic model DMCN and DMBERT, and NGS-BERT achieves comparable results with all the existing state-of-the-art models, including our previous work HMEAE, which shows the effectiveness of our NGS framework. This is overall experimental results on another dataset, the TechKBP 2016 competition. That is event argument extraction track. From the comparisons to the state-of-the-art systems and also the top performing models in the competition, we can observe consistent results with on the IS 2005. We further conduct ablation studies to show the effectiveness of each our designed component. Here two figures are to show the effectiveness of the simulated annealing. These are the F1 scores of our NGS-CNN model, changed with the iteration steps with and without simulated annealing in the Gibbs sampling process. We can see that the simulated annealing can not only speed up reaching the convergence, but also can improve the stableness of the results. And in this experiment, we show that the effectiveness of the prior neural network initialization. In fact, we know that the convergence of Gibbs sampling does not require a reasonable initialization. But in these experiments, we can see that a good initial state can also speed up the convergence. which is helpful in the application. In the last experiment, we want to study that if the improvements of our neural Gibbs sampling model really comes from the successfully capturing the event argument correlations, or just from some other factors. We split the 2005 development set into three parts, which contains different numbers of event arguments, and we observe the performance of our NGS-CNN model and its basic model DMCNN on them. We can see that with the increase of the event argument number, our improvements significantly rise, which shows that our improvements really comes from better modeling multiple argument correlations. To summarize, in this work, we propose the neural Gibbs sampling framework to model the joint distribution among event arguments. It combines the advantages of Gibbs sampling method and the effectiveness of neural network. To accelerate the convergence, we further introduce the simulated annealing. In the future, we can explore how to extend the neural Gibbs sampling framework to other tasks and scenarios, and we can see that although with the simulated annealing method, the neural Gibbs sampling model still requires about 100 times of inference. That is to say that how to further speed it up will be critical to the real-world application. Well, that's all. Thanks for the listening, and all the questions are welcomed. You can also scan the QR code to get our source codes, or contact me with this email. Thank you.